This is a video from section 12.1 and it's based off the lecture notes. We're going to start off with the Pythagorean theorem. Suppose we are given a right triangle. The legs of the triangle are A and B, and C is the hypotenuse. And so here's a picture of a right triangle. And I drew here the 90-degree angle. So this side is C. And we have A at the base and B along the side. And so the punchline is that A squared plus B squared is equal to C squared. Now let's take a look at the distance formula. Suppose P and Q are 2 points in the xy plane. Let D represent the distance between P and Q. And so I drew a picture of the xy plane. And I drew point P, which in this case is x1, y1, and Q, which is x2, y2. And what I want to do is I want to form a right triangle. And so that is here. So I draw a triangle right like so. Now, I need to have the coordinates of this point. Now, I go along the base, and I'm going horizontally along the base. So the x coordinate is changing. So I'm going from x1 to x2. But the y coordinate stays the same. And so the coordinates of this point that I'm highlighting here is x2, y1. Now, the distance between x1, y1 and x2, y1 from my picture is x2 minus x1. The distance from x2, y1 to x2, y2, right? Notice how the x-coordinate is the same, but the y-coordinate changed. So that distance is y2 minus y1. And so if I apply the Pythagorean theorem to get D, right, it pops out. So D is the square root of x2 minus x1 squared plus y2 minus y1 squared. So this is really an application of the Pythagorean theorem. And that's the distance between points P and Q. And this is where we're in 2 space. Now let's see if we can graduate to 3 space. Suppose P, which in this case is x1, y1, z1, and Q, which is x2, y2, z2, are 2 points in 3 space. Let D represent the distance between points P and Q. Let's come over here, and we have a picture. So over here we have P, over here we have Q. Okay? Now, if you notice, I formed a right triangle just like I did when we were in 2 space. And I claim the coordinates of this third point are x2, y2, z1. So we dropped straight down, okay? So the only thing that changed was the z coordinate. All right? Now, I need to find the distance between this point P and this third point. And so what I did is I took a look at these 2 points in the xy plane. But what does that mean? What I mean by that is I want to make the z coordinate 0, and that's exactly what I did here. So if you notice, if I take this point P and I project it down into the xy plane, that third coordinate is going to turn into a 0. And so I get the point x1, y1, 0. And then similarly, if I take the point x2, y2, z1 and project it down into the xy plane, I get the point x2, y2, 0. Now, the distance between those 2 points is really the same thing as what I did to find the distance between the points in the xy plane. So I'm just applying the Pythagorean theorem And I claim you're going to get this distance, which is the square root of x2 minus x1 squared plus y2 minus y1 squared. So if the distance between x1, y1, 0 and x2, y2, 0 is this square root, I claim that the distance between these 2 points up here is going to be the same thing. So in other words, it's going to be the square root of x2 minus x1 squared plus y2 minus y1 squared. So basically you're applying the Pythagorean theorem to get the distance between point P and this third point of the right triangle. I hope that makes sense. And then the distance between Q and that third point is just Z2 minus Z1. And so to get the distance between points P and Q, I'm applying the Pythagorean theorem again. So D is the square root of, and then in parentheses, I have the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. And it looks like that's the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. And that's how you find the distance between 2 points in 3 space. So I hope that's okay. Now, let's take a look at an example. It says, find the lengths of the sides of the triangle PQR. So this is a triangle in 3 space, all right? Is it a right triangle? If it's a right triangle, it must satisfy the Pythagorean theorem, and vice versa, by the way. So if you satisfy the Pythagorean theorem, you got to have a right triangle, and if it's a right triangle, the Pythagorean theorem has to be satisfied. And then the next part of this is it an isosceles triangle? So we're given points P, Q, and R. P is 0, negative 5, 5. Q is 1, negative 2, 4. And R is 3, 4, 2. So I found the distance between P and Q. I found the distance between P and R. Or you can think of this as the length of PQ. However you want to call it. Now, if it helps you, label your points. So like, for example, if I want the distance between P and Q, my x1 would be 0, my y1 would be negative 5, and my z1, let me kind of erase that. So my z1 would be 5. And then I have x2, y2, z2. And then I'm applying the distance formula. And if you notice, I get square root of 11. And then the distance between P and R, I claim is square root of 99, right? If you, again, apply the distance formula, you get the square root of 99, which is 3 times the square root of 11. So does that make sense? So I come over here, I take 3 minus 0 squared, 4 minus a negative 5 squared, and 2 minus 5 squared. And that's exactly what I did. And then I get 3 square root of 11. And then the distance between Q and R is the square root of 44. And that ended up being 2 times the square root of 11. Now, if you notice, if I take the length of PQ squared plus the length of QR squared, that does not equal the length of PR squared. So you notice 11 plus 44 does not equal 99. So triangle PQR is not a right triangle, and it's not an isosceles triangle either because 2 of the sides are not the same. So that's example 1. And it's right out of the Stewart calculus textbook, by the way. Example 2. It says, find the distance from the point 4, negative 2, 6, 2, and then in part A, we have the xy plane. Now, what that really means is we want a perpendicular distance. So, in other words, we want the distance from 4, negative 2, 6 to 4, negative 2, 0. That's a straight drop of 6 units. And I'm just going to apply the distance formula, okay? And if I apply the distance formula, I claim that the answer is 6. So that's the distance from 4, negative 2, 6 to the xy plane. It's a perpendicular drop. Now, in part B, I want the distance from 4, negative 2, 6 to the x-axis. But in reality, I want the distance from 4, negative 2, 6 to 4, 0, 0. That's the distance I want. And when it's all said and done, if I apply that distance formula, I'm going to get 2 times the square root of 10. And if it helps you, however it works, right, you can call 4x2, negative 2y2, and 6z2. And then we have x1, y1, z1. And then it's straight distance formula. And you get 2 square root of 10. Okay, that's going to do it for this video for section 12.1. My main emphasis in this video is the distance formula. We worked a couple of examples. And this is based off the lecture notes. Okay, thank you.